Alrighty, let's take a look at this KSP stuff, the solubility product constant. And this is the constant for the solubility equilibrium for slightly soluble or nearly insoluble ionic compounds. And when you put an excess of these salts in water, we end up with a saturated solution. And of course, we talked about that when you look at a saturated solution at the particle level, we have a dynamic equilibrium. Some of the solid is dissolving, at the same time some of it is precipitating back out of solution. It's an equilibrium, so we can write a K expression. These Ks are still temperature dependent. Keep trying to pound that into you that all these equilibrium constants are very temperature dependent. So here we see calcium oxalate, solid. When it dissolves, it'll break into the calcium ion and the oxalate ion. So when I write the expression, this is all I get. I just have the concentration of each of the ions because, of course, our reactant is a solid and we don't write solids in our equilibrium expressions. So for lead 2 iodide, it's going to break into the lead ion and 2 iodides. So when I write that expression, I got to make sure I include that 2, so I'm squaring the concentration of the iodide ion. And once again, KSP is still temperature dependent. Keep that in mind. Alright, so like we did with all of our other Ks, we can first calculate the K values. These are a little bit different because most of the time you'll see your solubilities reported in grams per liter. And when we want to go into the ice table, of course, we want to have it as concentration, moles per liter. So silver chloride's solubility is 1.9 times 10 to the negative 3 grams per liter. And of course, we have our magical 25 degrees Celsius. So to change that to molarity, I just need to divide by the molar mass of silver chloride, 143.4. So now I have the molar solubility, and I can use that information in an ice table. Again, if you're feeling confident, you can, once you are more comfortable with these, you can jump right to the equilibrium line, but we don't include anything about the solid, starting with 0, and then our change, of course, is plus x, and this is my x. So I just plug in 1.33 times 10 to the negative fifth for both silver and chloride. And when I do that, I get 1.7 times 10 to the negative 10th for the KSP. One more example showing some exponents involved. Lead 2 arsenate, found in some insecticides, its solubility is 3 times 10 to the negative fifth grams per liter. So first I need to change that to molar solubility. It's a fun molar mass, 899.4 for this lead 2 arsenate. Now when I set up my ice table, you have to be careful because this is x, and when I see my expression, I have 3x and 2x because of the balanced equation, because of how it dissociates. And so you have to make sure that you calculate x to plug into the expression based on those coefficients. So now the KSP expression, concentration of lead cubed, arsenate squared, and so we get quite a small KSP value. Now, just like we did, and we talked about with Ka and Kb and everything, there's always going to be a table of these values, and they'll always be given to you if needed. So calculating the K, while yes, we will do it, not as important as some of the calculations involved with K. Sorry. And so you see on this table, if you take a look at it in your book, there are some ridiculously small values, some very, very, very nearly insoluble salts. So barely any ionization. But if you look, there are some compounds that are definitely not on this table. And of course, which of these compounds are always soluble? The ones that I've asked you to memorize as far as solubility goes. Any sodium, potassium, ammonium, or nitrate salts are not on that table because they're completely soluble. And then, as it says there, when we know KSP, then we're able to do different calculations, more exciting than just calculating KSP. So first off, we can calculate the solubility. What is the solubility of fluorite, which is calcium fluoride, at our magic 25 Celsius, and we know the KSP. So when I set up my ice table, I end up with, at equilibrium, X for the calcium ion, 2X for fluoride. I know my K value, and so I just plug into the expression, and I see that my KSP is going to be equal to 4X cubed. And so I just have to solve that. Divide by 4, take the cubed root, and we get X is equal to 2 times 10 to the negative fourth molar. So that's the molar solubility. Typically, if it just asks what is the solubility, then you want to change it to grams. Or it might ask for the molar solubility, and you can stop there. But again, all I have to do is multiply by the molar mass, and then I can get my solubility in grams per liter. One last thing here, we can take a look at solubility in the common ion effect. Just like we did with the acids and bases, we can look at and see whether or not ionization can be repressed. And so here we see the equilibrium. Lead 2 chromate is slightly soluble in water. You see its KSP, pretty small. Well, what if lead 2 nitrate is added to this solution? Okay, and you'll see that that's the common ion effect. When we add lead 2 nitrate, all right, we are really just adding lead to this equilibrium. And so it's a Le Chatelier thing. Since the lead 2 ion is being added, poke, 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 it's going to shift to the left. And so more potassium, sorry, lead chromate precipitates out. Ionization is repressed. That's what we said when we were talking about the acids and bases, but here we would actually see precipitation. So the last thing here is we want to calculate the molar solubility of barium fluoride in water at our magic 25, then compare that to the molar solubility if it was put into 0.15 molar sodium fluoride. So first, the molar solubility of barium fluoride, my ice table. So I end up with X and 2X, and so it'll look very similar to the last problem. My K value is going to end up being equal to 4x cubed. And so I divide by 4, take the cubed root, and I end up with the molar solubility of 6.3 times 10 to the negative 3 molar. So now I want to do the same thing, but this time in 0.15 molar sodium fluoride. Of course, ignore the sodium, so I'm just using this 0.15 for the fluoride concentration. So that's my initial conditions, same change, and so at equilibrium, I'll have X and 0.15 plus 2X. My K value is the same. I plug into my expression, and the nice thing here again is because we're dealing with such small K values that I can just, ignore the X change in the expression. Okay, because of that, I can do the concentration divided by K or whatever is greater than 100. I don't have to worry about the whole quadratic equation here because especially these KSPs are so small, even smaller than our KAs and KBs in many cases. So now I can just simplify that expression and solve for X, and I get 4.4 times 10 to the negative fifth molar. And then the last thing, though, it asked us compare molar solubilities. Sorry. So on its own, barium fluoride had a molar solubility of 6.3 times 10 to the negative 3. In the presence of that sodium fluoride, 4.4 times 10 to the negative fifth. So it was 140 times greater without that fluoride present. That's how much it was repressed when the common ion effect was involved. All right, that'll do it for now, and I will see you soon.